Class 11th Chemistry. We were discussing Unit 9 Hydrogen, and in this video we will discuss about hard water, temporary and permanent hardness of water. Hard water. Water which does not give lather with soap is known as hard water. Reason for hardness of water: presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride, and sulfate in water makes water hard. Soft water. Water which gives lather with soap easily. Water free from soluble salts of calcium and magnesium is called soft water. Hard water forms scum, that is precipitate, insoluble substance with soap. As we know, soap is the sodium salts or potassium salts of higher fatty acid. Okay, and if we consider the soap containing sodium stearate, that is C17H35COONA, it reacts with hard water to precipitate out calcium or magnesium stearate. Reaction is 2C17H35COONA. This is a soap molecule. This M2 plus, where M, it may be calcium or magnesium ions which are present in the hard water, and after the reaction we will get this, that is magnesium or calcium salt of stearate, which is insoluble. This downward arrow represents the formation of precipitate. Okay. Hardness of water is of two types: temporary hardness and permanent hardness. First come to the temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonates. This hydrogen carbonate is also known as bicarbonate. Okay. It can be removed by boiling. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium hydroxide, and calcium hydrogen carbonate is changed to insoluble calcium carbonate. These precipitates can be removed by filtration. Reaction can be represented like this. This is magnesium hydrogen carbonate. On heating, it gives magnesium hydroxide, which will get precipitate, and carbon dioxide is in gaseous form, which evolved. If we heat, that is on heating, calcium hydrogen carbonate will decompose to give insoluble calcium carbonate along with H2O and CO2. Another method to remove the temporary hardness of water is Clark's method. In this method, calculated amount of lime is CaO, okay, is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Actually, when we dissolve this CaO into the water, this will convert into calcium hydroxide. Okay, and then this calcium hydroxide reacts with the calcium hydrogen carbonate and magnesium hydrogen carbonate like this. Calcium hydrogen carbonate react with the CaOH twice to give precipitate of calcium carbonate along with water. The same way, magnesium hydrogen carbonate, when react with the CaOH twice, it will give the precipitate of calcium carbonate and precipitate of magnesium hydroxide along with the water. Now, permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following methods. First method, treatment with washing soda, sodium carbonate. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonates. Reaction is this. MCl2 react with the sodium carbonate, and this will form insoluble MCO3 plus 2NaCl, where this M may be magnesium or calcium. In the same way, MSO4, when react with the Na2CO3, we will get the precipitate of MCO3 plus Na2SO4. Another method to remove the permanent hardness of water is Calcone's method. Sodium hexametaphosphate Na6P6O18, commercially called Calcone,
when added to hard water, the following reactions take place. First of all, Na6B6O18 gives this ion, Na4B6O18 2 negative. And when this ion react with this calcium or magnesium ion present in the hard water, it will form this complex. Okay, and this M stands for magnesium and calcium. The complex anion keeps the Mg2 plus and Ca2 plus ions in solution in this complex. Simply we can say Mg2 plus ion and Ca2 plus ions which are free. Now they are present in the form of this complex, and they will not give the precipitate with the hard water. Well, they will not give the precipitate when react with the soap. In this way, we will get the soft water. Next method is ion exchange method. This method is also called geolite or permuttite process. Hydrated sodium aluminium silicate is called geolite or permuttite. For the sake of simplicity, sodium aluminium silicate, that is NaAlSiO4, can be written as NaZ. When this is added in hard water, exchange reactions take place, and this reaction can be represented like this NaZ, this M2 plus, where M is calcium or magnesium present in the hard water. So from this geolite, sodium is exchanged with the calcium ion and magnesium ion. Okay, and we will get Na plus ion in the water. This geolite process can be represented like this diagram. Permuttite or geolite is said to be exhausted when all the sodium in it is used up. So it is regenerated for further use by treating with an aqueous sodium chloride solution. This is the reaction for the regeneration. Okay, this is treated with the NaCl. Again, we will get NaCl. Now try to understand this diagram. This, we can say, this is the geolite bed. Okay, and from this we are passing the raw water, that is hard water, and this concentrated NaCl we are using for the regeneration. See, in this, first of all, calcium and magnesium ions are present in the chloride and sulfate form, and after passing through this geolite bed, we will get the NaCl and Na2SO4. We can say calcium and magnesium ions remained in this geolite, and we will get the soft water which contains sodium salts. Another method, synthetic resins method. First of all, what is this resin? This is a sticky substance that is produced by some trees, like we can say gum. This is one resin. In the same way, when resin is synthesized in the laboratory, then that is known as synthetic resin. It may be a kind of plastic. Okay. Nowadays, hard water is softened by using synthetic cation exchangers. Synthetic cation exchangers. That is, we can say cations like calcium and magnesiums are exchanged by the sodium. This method is more efficient than geolite process. Cation exchange resin contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin, represented as RSO3H, is changed to RNA by treating it with NaCl. The resin exchanges Na plus ions with Ca2 plus and Mg2 plus ions present in hard water to make the water soft. Here R is resin anion. Reaction can be represented like this. This is RNA from synthetic resin. This M2 plus, that is calcium or magnesium ion present in the hard water, and after the exchange of these cations with Na, we will get Na plus in the water. Again, the resin can be regenerated by adding aqueous NaCl solution. Formation of pure demineralized or de-ionized water. Now, first of all, what is this de-ionized water? It is free from all soluble mineral salts, okay, and is obtained by passing water successively through a cation exchange in the H plus form and an anion exchange in the OH minus form resins. First of all, in the cation exchange process, hydrogen ion exchanges for Na plus, Ca2 plus, Mg2 plus and other cations present in water, and this reaction can be represented like this. This is cation exchange resin. These are the cations present in the water, okay, and after the reaction we will get H plus in excess. So this process results in proton release and thus makes the water acidic. Now this acidic water is passed to the anion exchange resin, and in anion exchange resin OH minus ion exchanges for anions like Cl minus, HCO3 minus, SO42 minus, etc. present in water. This RNH2 when react with the H2O, this will convert into RNH3 plus OH minus. This is our anion exchange resin, and with this anion exchange resin is treated with the water containing anions, okay, then whatever the anions present in the water are replaced by the OH minus ion. Clear? Now OH minus ions thus liberated neutralize the H plus ions set free in the cation exchange, and we will get the pure water H plus plus OH minus ion, and we will get water. Now you can see this diagram. Okay, this is indicating demineralization process or ion exchange process. Now in this case, the exhausted cation and anion exchange resins beds are regenerated by treatment with dilute acid and alkali solution respectively. See the diagram. This is cation exchange column. Clear? Now in this case, this is the cation exchange resin. When we pass the raw water containing the cations and anions, okay, then this is the water containing these Ca and Na ions. When this is passed to this cation exchange resin, we will get the SO42 minus and Cl minus ion, and Ca2 plus and Na plus are replaced by this H plus ion. So we will get the acidic water. Okay, and when this acidic water is passed to the anion exchange column, okay, then these anions SO42 minus and Cl minus ion, these are exchanged by this OH minus ion. So when H plus from this and OH minus from this will react, and we will get the H2, that is a demineralized water or a de-ionized water. Okay, and this dilute HCl, this is used to regenerate this cation exchange resin, and this dilute NaOH is used to regenerate for this regeneration of this anion exchange resin. Clear? Thank you. Subscribe my channel to get the next video from this chapter.